Good afternoon, everyone. Welcome to Taco Tuesday, commercial focused. Brett Zerva here, and I am high above courtside in Cranston, Rhode Island. Actually, that's a Johnny Most thing. That maybe not anyone realizes who I'm talking about, but I'm not high above courtside, but I am in Cranston. I'm at the home office today instead of being on the road or at home or something. We have a group in for some training this week. Dave says, good afternoon. Good afternoon, Dave. That's a good sign. I think that means people are hearing me. Anyways, so that's a good sign. And I'm sure you see the introduction screen that is on the posted as well. If someone can't see that, let me know. Before I get too far into it, there is one handout available. So as my new coworker here, well, he's not that new anymore. He calls it a slide deck. I call it the presentation. But anyway you look at it, there is one handout, and it's all of the slides or screenshots that you're going to see. It's a PDF version of it. PDF, Dave says. PDF, that's what it is. Okay, we got a Taco, privately held company, third generation, over 105 years old, headquartered in Cranston, Rhode Island. Hopefully, some of you folks, I know some of the names on here, can come visit us someday. We have a lot of classes out here on an ongoing basis, both residential focused, residential/wholesale focused, and commercial focused. Get in touch with your local reps or sign up for some of the classes we have available that you can come and visit us. We love to have visitors. That is one of the mantras of our owner of our company, Mr. Johnny White. He says, show this company to as many people as you want and invite them in. If they can give us time, we can accept their time and give them a nice and enjoyable visit. Educational and fun. Educational and fun. Because if it's not fun, he says, let's not do it. So most of the time it is fun as well as educational if you come visit us. So today's presentation is going to be done. The main presenter will be Tony first. He'll introduce himself very shortly. It's a topic that has a lot of interest based on the registrations I see. So I'll let him get into it very, very shortly. About 24 hours from now, you'll get an email. Some of you have been through this before. And that email will have a link to the presentation. It is being recorded, so keep that in mind, as well as a downloadable PDF certificate for your 1-hour presentation. Excuse me, PDH certificate. I'm not sure if I said that right the first time, so you can get that through that as well. You do have to be present during this webinar in order to get this certificate. If you sign up and in the future for some of ours and you don't sit through it, then we can't give you the PDF, the PDH certificate. That's just one of the rules that we have internally here, as well as I know you can watch it, but we need you to be able to view it live. So anyways, that's enough yapping. Good history here at Taco. We've been in this building since 1953 or sooner or earlier than that. Believe it or not, back in the original, our production area, its main use way back, it was built as a trolley. Some of you folks don't even know what a trolley is, repair barn. So, before there was vehicles, there was trolleys that going up and down the street that were our facilities on, going through 3 or 4 different cities. And those trolleys would come in here for maintenance as well as upkeep and various other stuff, believe it or not. And then Mr. Ford and others came up with the automobiles, and that trolley business kind of went away. So this building became vacant, and Johnny's dad purchased it quite a few years ago. So how about that? That's an insight that not everybody knows. Not everybody knows that. So anyways, and we have some guests. Like I said, we have some guests in today. And today's Tuesday, right? So we're having tacos at Taco on Tuesday. What do you think of that, huh? Tacos at Taco on Tuesday. Man, oh man, how about that? How about that? And they were pretty good. They were pretty good. So, anyways, I think that's enough yapping for this morning. I always like to talk a little bit just to give some people some time to get in here, but I do want to turn it over to Tony now. So, Tony, I will be monitoring the questions, but other than that, Tony, take it away.
Thanks, Brett. So, welcome everybody. As Brett said, sometimes we get to be out on the road. I spend most of my time on the road training. I'm in wonderful Tucson, Arizona this week. I'm doing some remote TakeOU stuff. I'm in Tucson today and tomorrow, and then I head to Phoenix for TakeOU on Thursday in Phoenix. So all of you out there that are served anywhere in North America, if you want us to come to you because you can't make it to us, reach out to your local TakeO rep. And that's what I do, is I run around the country doing the exact same thing. I do teach all kinds of classes. So we're all about educating people. We want people to really understand hydronics and how hydronic systems work. So with that, today we're going to talk about induction and permanent magnet motors and what's similar and what's different. And we're also going to touch a little bit about ECMs as well, but that's where our focus is today. So we're going to start out, we're going to talk about the induction motor, what it is. Then we're going to talk about permanent magnet motors. We're going to talk about what's different, what's similar between the two. We're going to talk about the ECM, or the electronically commutated motor. And we're going to talk about what's different between an ECM and a permanent magnet AC motor, because there is a difference. Okay. So anyway, let's get started with electric motor technology. So if we look, way back when Nikola Tesla invented the induction motor. And the induction motor is basically, the principle of induction is that when a force is applied to a conductor, okay, that force being the black arrow in there, which is force or current, is applied to a conductor, it causes it to move through a magnetic field, and an electromotive force is generated within the conductor. And if that conductor is a closed circuit, current will flow. Okay, that's the simplistic explanation of an induction of electromagnetism. Okay, so what happens is by passing this electric current through the windings of the motor, there's a force that's generated. Okay, and so that current is passing through that conductor, the copper windings of the motor, and it creates a magnetic field. That magnetic field causes movement of another conductor, okay, which is the rotor. So that's the way a motor works, is it's basically a giant electromagnet, okay? In an induction motor, that magnetic field is generated in the stator, okay, because we apply electricity to the stator windings. That creates a magnetic field, and it induces a magnetic field into the rotor, which causes the rotor to want to rotate. Okay, and the conductor is the F in the illustration. That's that bar. That is the rotor in any given motor. Okay, so if we look at a cutaway of what an induction motor looks like, so induction motors use the electrical energies from the AC supply to generate the, hang on a second here, I got to fix a little something on my screen. It generates the rotational forces and to induce the rotor's magnetic field, because when we apply that electricity to the stator windings, there's three sets of windings in there around the 360 degrees, and that magnetic field rotates in those three windings. And then that induces a current in the rotor and then causes the rotor to rotate as well. Okay, so out here you can see where the arrow is pointing to, that is the stator, that's the copper windings, the steel laminations, and that is a giant electromagnet. That's all it is. There's no magic there, I promise, there really isn't. And then we have the rotor, and again, that is steel and copper, and we induce a voltage or a current in that rotor, to create the magnetic field, because there are no actual electrical connections between the power source and the rotor. It is all induced current. Okay. So what we have to do is we look at a typical three-phase motor. We have three phases, and we have three phases in the rotor and three phases in the stator. And the two rotating fields are slightly out of sync from one another, and the rotor is constantly chasing the magnetic field in the stator. Okay, so it's always, you know, magnets oppose, like in north and south and all that. You're creating the magnetic field, and so it's causing that rotor to constantly move because it's trying to chase that magnetic field in the stator. Okay, and so it continuously moves, and that's what causes the rotation within the motor. Okay, so we create torque by that interplay between those two magnetic fields. That's what creates the torque inside the rotor, inside the motor. Okay, so we have a magnetic field rotating in the stator. We have another magnetic field rotating in the rotor because the motor is actually rotating, whereas the magnetic field in the stator actually rotates electrically because of the way AC current works. Okay, so that's a conventional permanent magnet motor or a conventional induction motor. Okay, when we move into the realm of permanent magnet motors, what happens is that what we do is we take the rotor and we take the conventional rotor out of the motor, and we take the copper and the steel and everything off of it, and we mount rare earth permanent magnets to the motor, to the rotor. Okay, they're encased in epoxy, and they're epoxied to the rotor with a high strength epoxy, and that creates a permanently magnetized rotor. Okay, so now all we have to do is we create the stator field with our VFD. Okay, and now because the rotor is permanently magnetized, we don't have to waste any energy in creating that second magnetic field inside the rotor. Okay, my computer is giving me fits today. There we go. So we have our copper windings in the stator, and then the rotor, we have high flux permanent magnet motors, and it's an intrinsic magnetic field. So that rotor field is always there. So even if I take that motor and I turn the power off to it, and I pull the rotor out of it, that rotor is still magnetized. Okay, so it's always a magnetic field. And this presents some interesting challenges for people that rebuild motors, because now they have to be careful when they take that motor apart. That is a giant magnet that they're removing from that motor. Okay, I've played with some of these, I've taken them apart, and if there's anything steel anywhere in the area where you take that motor apart, that rotor will find it. It will attach itself to whatever piece of steel is anywhere near you. Okay, so we have to start thinking about where this makes sense in our industry. Okay, they make permanent magnet motors up to, I think the biggest one I've seen so far is 100 horsepower. They are real common in the smaller horsepower ranges, and part of the reason they are more common in the smaller horsepower ranges is that they are more efficient than either NEMA Premium or NEMA Ultra Premium motors. Okay, if you look at a 1 horsepower permanent magnet motor, it's about almost 12% more efficient than a conventional ultra premium motor. Okay, I should say, let me rephrase that. The ultra premium is the permanent magnet. The NEMA Premium is the conventional induction. It's the high performance induction motors. But you'll notice that in the small sizes, that ultra premium motor, the permanent magnet motor, is more efficient. The problem is, as you get bigger and bigger, the gains in efficiency start to fall off, okay? And once you get above 10 horsepower, it's about 2.5 to 3% more efficient in an ultra premium motor than it is a conventional induction motor. So the efficiency gains aren't as dramatic the bigger you get. It's not to say that they're not good, and it's not to say that they're not better, but understand that the efficiency gains aren't as dramatic the bigger you get. So if I look at this, and where this is really important to understand is understanding that permanent magnet motors don't lose as much efficiency as we reduce the speed, okay? Unlike a induction motor, okay, that loses more efficiency the slower we go. That induction motor starts to get less efficient. Permanent magnet motors don't have that drop off in efficiency until you get down around 30% of design max speed. That's when they really start to lose their efficiency, okay? Whereas an induction motor, about 55 or 60% of design max speed, the efficiency starts to go, and as you get down below 30%, it really falls off to next to nothing, okay? So when we look at this and we look at the different technologies, the biggest thing we've got to understand is that permanent magnet motors and brushless servo motors are both synchronous AC starting, whereas an induction motor is asynchronous starting, okay? What that means is that with asynchronous starting, I can have an across-the-line motor starter, and I can start that motor up by pulling a contactor in, and that motor will start. It doesn't care because it induces the rotating magnetic field into the rotor, so I don't have to get the two magnetic fields lined up to allow that motor to spin. With a permanent magnet or brushless servo motor, I have to get those two magnetic fields lined up before I can allow that motor to rotate. Otherwise, it won't rotate, okay? So what happens is on a permanent magnet motor, I have to have a VFD on a permanent magnet motor. So with a permanent magnet motor, I cannot hook that up and run it across the line like I can with an induction motor, okay? So we have to understand that. And when you look at a permanent magnet motor and watch it start, it's a little weird when you watch it start, because what's going to happen is that motor, when we first apply power to it, the stator's going to walk back and the rotor's going to walk back and forth a little bit till it gets everything lined up with the magnetic field, and then it'll start to rotate. But for the first second or two, you may see it and you think it's locked up, and it's not. It's trying to figure out where the magnetic fields are to get them lined up before it allows it to rotate. And it has to do that every time that motor starts. So it's a little bit unusual, it's a little bit different, but once you see it happen and you understand what is happening, it makes sense, okay? So the big differences: synchronous motors operate at a constant speed, unless you put a drive on them. They need that external DC excitation to start. So what happens is, that's part of what's happening is we're applying a little bit of DC current to the motor, figure out where the magnetic fields are, and get everything lined up, okay? Their rotors have permanent or electromagnets, okay? That's what's going to cause, that's what the big difference is. Synchronous motors are generally more energy efficient. They are smaller. Asynchronous motors are simple, durable. You know, they've been around forever. Everybody understands them. There's nothing real complex about them. And they're relatively low. Both motors are relatively maintenance free. You still got to maintain bearings. You still got to keep the dirt off of them, because you got it. They're cooled by air. So none of those things change any. The big difference is in the starting technology and the way the rotor is built. The other thing that you will notice with permanent magnet motors is they weigh less. Since we've taken all that steel and copper out of the rotor and replaced it with rare earth permanent magnets, they weigh less. On average, about 30% less, which is a good thing. And you know, we're always trying to figure out how to make equipment weigh less, because it's easier to handle, easier to maintain, takes less structure to support that equipment. So making it weigh less is a good thing. Now, one of the things I have found, though, in talking to some of the cooling tower guys, is they found that on the very large frame permanent magnet motors, they've actually gotten bigger. So the motor itself is bigger, so they've had to do some redesign on some of their supporting structure to support those big motors. So in any motor, when we're going to change its speed, unless we have a multi-speed motor, we're going to use a variable frequency drive to change that speed, okay? And in that variable speed drive, we have the rectifier circuit, a DC bridge, and an inverter circuit. The rectifier circuit is on the far left-hand side, and this one is a 6-pulse drive. So I've got 6 rectifiers in there, 2 for each phase, okay? And 3 of them are on the top half of the phase, 3 of them are on the bottom half of the phase, okay? Then we've got a DC bridge, and the DC bridge is what couples everything together. And then we have the inverter section, which is taking the DC power, because we're in the AC side, we're going to go from AC power through the rectifiers into DC power, across the DC bridge, into the inverter, and the inverter is going to take that DC power and turn it back into AC power and send it out to the motor, okay? And by doing that, a asynchronous motor, the motor lags behind the stator field, okay? The rotor lags behind the stator field, and that's what's creating that rotation, okay? And again, like I was saying, when we start up a synchronous motor, we have to get those 2 magnetic fields in alignment before we allow it to start. And that's why it's imperative that you have a VFD attached to that synchronous motor or that permanent magnet motor, because of that need to get those 2 fields lined up. Okay, so how do we go from electronically commutated motors? What's the difference between that and a permanent magnet AC motor? Okay, so first of all, let's understand something. All ECM motors are permanent magnet, but not all permanent magnet motors are ECM. Okay, that's the big difference. So if we look at the definition, commutated means to reverse every other half cycle of an alternating current. That's what it means. So if we look at that, ECM motors operate with an AC power source, okay? Just like a permanent magnet motor does. They both operate with AC power. The difference is that in an ECM motor, we're going to take that AC power and turn it into DC inside the motor, okay? And inside there, everything is DC. Once you get past the AC connection, go through the speed controller, everything else is DC inside that motor, okay? So it's a different style motor than what an AC induction motor is, okay? So when the rotor turns, the brushes connect with the next section of the commutator. And this is a conventional DC motor that has brushes in it. Now, in today's world, we don't use brushes anymore. We're going to talk about that in a minute. Brushes were the downfall to DC motors, is the brushes always wore out. And what these brushes do is as they connect to each section of the commutator, it reverses the magnet's polarity, okay? And that's what causes the rotation, okay? And the motor keeps turning that way. It's really simple. You know, way back when I was in high school or junior high school, we had shop classes, and we actually built a DC motor in shop class. You know, did all the windings, and if you didn't get your windings right and didn't get them tightened up and neat enough, the motor wouldn't turn. And so that was way back when. We won't talk about how many years ago. It was in the dark ages. We were still learning off of stone tablets. Anyway, so when I look at a new style motor, which is a brushless DC motor or a BLDC, you're probably all familiar with brushless DC motors and you don't even realize it. If any of you've gone to any of the big box home center stores, you know, the orange one or the blue one or the green one, take your pick. They sell all kinds of electric power tools. And you can buy a battery drill, and you can buy battery sawzalls and chainsaws and all that kind of neat stuff. And you'll notice all of them talk about being brushless. Brushless motors are more durable. You don't have to worry about replacing the brushes. You don't have to worry about the brushes failing on you. They've gone to this electronic technology or brushless DC motor technology. And so anyhow, you've got 3 coils in there, 3 sets of coils, and each coil is wound in a different direction, clockwise and counterclockwise. Okay. And then we've got permanent magnets embedded on the shaft. Now, in this particular example, it's not the shaft. This is a rotating housing. So the shaft is stationary, and the rotating part is the shroud. Just a different type motor technology. These are real common in ceiling fans. So in ceiling fans, the shaft is locked, and the housing actually rotates, because the shaft is where, like your light set and all that stuff is mounted to, and that's what's attached to the ceiling. It's the shroud around it that rotates. So that's the way a ceiling fan is set up.
Hey, Tony,
Yes, sir.
we have a question here, and I think it's a good one to bring up right now.
Okay.
So an ECM motor is DC motor? Kelvin's asking that.
Yes, ECM motors are actually DC motors. Okay, even though you got AC power applied to them, internally what's going on inside that motor is all DC power.
10-4.
So that's why I say all ECM motors are permanent magnet, but not all permanent magnets are ECMs, because you can have permanent magnet AC and permanent magnet ECM, which is a DC motor. Okay. Now, in an ECM motor, we always have more magnets than we have coils. Okay. And that's make sure we keep everything rotating. Okay. So each group of coils is supplied with DC current from the electronic controller. Okay. And this is really important to understand this. So if you look at the picture, you can kind of see the 3 different sets of power connections: the red, the black, and the yellow. Those are each set of coils that are powered by DC power. Okay. And what we actually have is we have electronics in there, and we have these wonderful little transistors or high-speed switches. So this transistor is nothing more, the simplest way I can describe it, it is nothing more than a high-speed switch. That's all it is. It's a high-speed switch. It is a light switch that turns on and off really quickly electronically. And so what we're doing is that's how we are commutating or changing and rotating the magnetic field around, is we're changing the pulsing going to those switches, okay, or pulse width modulation. We're changing how fast or how long those pulses last to change what we're doing to the motor. Okay. Okay. So what we end up with is we have one coil attracts the opposite poles and one coil repels the like poles. And that's what causes the rotation inside the motor. Is it works on the basic principle of magnetism that opposites attract and likes repel. It's that simple. There is nothing magic going on. There's nothing oddball. And all motors, by the way, all motors work by the exact same principle of magnetism. Okay, it's just how we create that magnetic field. That's the big difference. Is how we create the magnetic field in the rotor and how we create it in the stator. So what happens is we go along, and as the field continues to rotate, we just cause the rotor to move. It's that simple. Okay, and as we go along, it just continues its merry way as we rotate around. And the difference is with ECM motors, we always know where that shaft is at. Okay, there's technology built in there. It gets into the IP of how we build the motors. But what we know is we know where that shaft is at any point in time. We know what position it's in from 0 to 360 degrees. So we know where it is all the time. Okay. So the thing we got to understand is there's a huge change coming within our industry, starting in next year. There is a mandate on circulators that we're getting away from induction motors and moving over to ECM motors. Okay, so we're way ahead of the game. We've got most of our circulators. Some of our other guys that deal with the circulator stuff a whole lot more can tell you the exact numbers, but Brett, you may know them as well. How many of our circulators we've actually got converted over? I think it's the bulk of them at this point. We've converted them over to ECM motors, haven't we?
We are making both, but quite a few of them have been transitioned and are available, correct?
Yep. And so the big change is that starting next year, by the end of next year, all circulators have to be ECM style motors.
I thought it was 28, but I forget the exact date. Anyway,
maybe it's 27. Since I don't play in the circulator world much, I don't keep track of all that.
Yep.
So what kind of questions we got there, Mr. Brett?
All right, so I've got one question, unless some others pop up. Kelvin's asking, this is a question that's great for motor people. What is brake horsepower? Why do some companies use brake horse on their chart and some use horsepower?
So the reality to this is, okay, so horsepower is the amount of work that motor can do with full power and full speed. Okay, that's it. Rated horsepower, rated speed. That's the way the motor is built. Brake horsepower is because there are losses in every motor. Okay, so there's losses due to because there's no perfect power conversion. So we apply power to it. Some of that energy goes to create the magnetic field in the stator, some goes to create the magnetic field in the rotor, and then there are windage losses because you've got a fan on the outside of that motor circulating air. There are other losses within the motor because it's not perfect. And brake horsepower is the amount of work that the device is actually doing. That's how much power that device is actually consuming. And generally speaking, you want about 30% reserve. And if I remember correctly, HI is 30% reserve. I'd have to go back and look at my HI manuals. But there's about a 30% reserve. So that your actual motor horsepower has to be about 30% greater than the required brake horsepower. And so, one of the things that I always look at when I look at pumps, and somebody says, "Oh, my pump's not working correctly, or it's not providing the right head, or whatever," I go and look at the differential pressure across the pump, and I plot it on the pump curve, and I look at what the absorbed power or the brake horsepower is supposed to be at that point, and then I'll calculate, is it really at that point? Because that tells me a whole lot more about whether that pump is really operating on its curve where it's supposed to be. And the other thing we have to understand is as we change speeds, the absorbed power changes as well. Okay, that's why VFDs do what they're doing, is because they're changing that absorbed power amount. They're not changing the horsepower of the motor, they're changing the absorbed power. Okay, because it's still a 30 horsepower motor. But as we change the speed, if we drop the speed by 10%, that's a roughly 27% reduction in absorbed power.
All right, so I got Steve's asking, can you talk a little bit about the OE package? I'm confused. If this is ECM or not?
So the OE package is a permanent magnet AC motor. It is not an ECM motor because it has a conventional VFD on it. And the only difference is that motor is a permanent magnet motor.
Why do ECM motors cost so much? Do they ever pay for themselves? The $64,000 question. Bill's
Well,
always practical with his questions, you know?
well, the reality is that yes, they will pay for themselves eventually. And now that all of us that manufacture circulators are going to ECM motors, the fan guys have been using ECMs for quite a while in fan motors. And as that motor technology has improved, the production costs are coming down. And therefore, I think as time goes on, the production costs will get better, get more in line, and you won't see the cost differential. And they will start to, you know, the payback will get better.
All right. What is the source? This, I don't think you and I can answer this one, but I'm going to ask the question anyway. Kirby's asking, this is kind of off the wall a little. What is the sourcing of the rare earth metals, and is it economical for TACO to use recycled material? Is new recycling networks being set up to recover these rare earth metals? We don't make the big motors. We don't make here. We buy them from motor manufacturers. We do wind the smaller ones, fractional horsepower. But you want to add anything to that question/statement, Mr. Tony?
Yeah. So what I know from my little bit of research into recycling and all that, yes, there are facilities that do recycling on the rare earth stuff. I don't know how widespread it is. I think part of the problem we have is that if you think about it, there is a bigger market right now for lithium-ion battery recycling than there is anything else. And so there are some rare earth elements in lithium-ion batteries. The rare earth magnets, however, I don't know that the industry has enough of them out there enough and have had enough failures that they have to be recycled yet. I don't think we've gotten to that point. You know, it's easy to recycle conventional motors because there's a whole bunch of them out there and they've been in use for so long that they're always failing and they always get recycled. With a permanent magnet motor, you know, you can still recycle the steel. You can still recycle all the copper for the stator windings. The rotor is where it becomes a challenge. And I don't know, right off the top of my head, of anybody of a defined program for recycling that. Now, I'm not saying there isn't one. I just don't know about it.
There's a business model down the road for Kirby and others to think about.
Hey, Brett, maybe that's our retirement business model.
No, I'm fishing when I fishing and gardening and hiking and other stuff. All right, here's another good question. For AC, I haven't read it, so I'm reading it for the first time. For AC
Okay.
motor with VFD, first the AC comes in VFD, it turns into DC, then the output turns back to AC again?
Yes, that's exactly what happens. So
Then, go ahead.
what you have to
I'm going to
understand
finish his question once you finish your statement.
Yeah. So the VFDs take AC power, three-phase or single-phase AC power, convert it to DC through the bridge rectifier. Out of that bridge rectifier, it goes to the input side of the inverter, and the inverter section turns it back into what we call manufactured AC power. And that AC power in turn then goes to the motor. So it manufactures a sine wave. That's how it is creating the variable frequency on the output side, because the power coming in is still 60 hertz power.
So the rest of his question is why the 460 volts AC motor doesn't run when your source lesser than 460 volt, or we can vary AC source to speed up or slow down the speed. I'm not sure I understand that
Okay.
that well.
So So when you have a 460 motor and a 460 drive, I have to have 460 volt AC power coming into that drive. I can't put 230 volts into that drive and get the drive to turn a 460 volt motor, because that motor still has to have 460 volts. Okay. What you have to understand is that the drive doesn't manufacture voltage. It manufactures frequency. And yes, the voltage does change, but the voltage change is not as dramatic as the frequency change. Okay. And I took a whole bunch of slides out of this deck that kind of talked about this stuff. I should have left them in, Brett, that talk about VFDs. And the reality to VFDs, maybe this is another good webinar topic, is we do one on VFDs. Since we were just talking this morning about what to do for next year. What happens is you have to understand that power cycles, you know, the AC waveform, that AC waveform on the output side of a drive isn't really that nice sinusoidal waveform that we're all used to seeing. Okay, it is much choppier. And unfortunately, I don't have that slide readily available, but I've got a really good picture of what that slide looks like, because that waveform looks much different on the output side. And so what we're doing is we're changing the frequency. So instead of 60 hertz, the output is something else. It's slower. So that's what's dropping the speed to the motor. But as we drop that frequency, we drop the power a little bit, we drop the voltage a little bit, but it doesn't drop as dramatically as going, you know, you couldn't put 230 volts into a 460 motor and get the motor to actually do anything. It'd just sit there and look at you and go, I don't know what to do.
I can relate. I don't know what to do. Why? I don't know if you have the answer to this one, but maybe you can make something up. Why in the air conditioned industry always use DC inverter motors nowadays?
So it's all about energy efficiency and variability for speed. So the reality is we've been doing it on fans for quite a while. We're now doing it on compressors, and it's all about understanding load and matching your equipment capacity to your actual load. So you kind of have to understand that we design buildings, and when I do a load calculation on a building, I design to the ASHRAE 1% condition. Okay, and what that means is that 1% of the time it's at that condition. Okay, but I got to make sure the HVAC system meets the load in that ASHRAE 1% condition. What that means is that 99% of the time, the system is operating at less than full load, because I'm not at full load conditions outside. I don't have full capacity of people in the building. If I think about buildings and I think about the load imposed on that building, okay, I don't have maximum occupancy in that building because I design occupancy based on so many people per square foot. Okay, I have an outdoor condition. What's not always at that condition. It's at, you know, sometimes it's cooler, sometimes it's warmer. You know, it may be colder, maybe warmer, but I design for those far extremes. The bulk of the time, 90% of the time, an HVAC system operates at 60% or less of full capacity. ASHRAE did a study on this a number of years ago, and that's the numbers they came up with. Well, if I don't have variable speed equipment, then what happens is I lose efficiency. So to give you a really good example, a chiller, as I decrease the delta T to the chiller, my chiller efficiency drops off. And so if I can keep my delta T up by adjusting pump speeds and water flow, I can adjust compressor speeds, I can adjust cooling tower capacities, all of these things by having variable speed motors everywhere, I can closely match the amount of cooling output to what the building actually needs. Same thing with heating. I also do a much better job dehumidifying the building, because now I don't have this grossly oversized air conditioner and it comes on and it drops the sensible load, but it doesn't have a chance to dehumidify. Well, if I can slow everything down and closely match the load, I can do a much better job of dehumidifying the space. Does that make sense?
Yep. It's very important to, I mean, a lot of people have that trouble with their homes where they don't have the right setup on their equipment at home, and they don't dehumidify, so it seems clammy. Anyways, VFD question. Can we run the pump motor over 60 hertz as long as we don't over motor VLA? We don't FO over motor.
Yeah.
Bill, you might have to clarify that, but I think you understand what this question is.
Yeah, so the reality is, so what we have to understand is, as we speed is directly proportional to flow in the case of pumps and fans. But we have to understand that horsepower goes up and down by the cube. Okay, so as I start to go above 60 hertz, horsepower is going to go up as well. So it's not just, it's understanding that you're going to run out of horsepower really quickly. And generally speaking, most of the pump guys, most of the pump manufacturers, we all look at it, and if that pump was designed as a 60 hertz motor at 1750 or 3600 RPM, whatever the speed range was for that motor, we don't typically want to go more than about 63 hertz. And you got to be really careful, because you will run out of horsepower really quickly and you will overload really quickly. You also have to remember, out at the far right-hand side of that curve, I can't tell you what that pump is going to do. You got to be really careful about how far you go out past the end of the curve in the speed range, because that starts to get unstable out there. That impeller wasn't designed to run out in that range. Fans are a little bit different. Fans, a given fan wheel could be designed for a whole lot of RPMs, and also because air is compressible, unlike water, it behaves differently when I increase the fan speed. Now, yes, there are permanent magnet motors out there that we can take much higher, but those pumps are specifically designed to run with a permanent magnet motor with a very, very wide speed range.
Yeah, I always tell people, if you want to go above 60 hertz, contact your TACO rep, who will contact the factory to make sure. It's very difficult to give a blanket statement to some of those outside the norm questions.
Yeah.
To be quite honest, I get nervous when people take it across the board as the way to go. It's always better to be safe than sorry.
Exactly. And it's all about understanding the pump curve. Where is the pump operating on the curve currently? Where do you anticipate it to be operating at? Understanding, let's say it's a 30 horsepower motor and you're using 27 brake horsepower at the design point, and you want to overspeed it. You just don't have enough horsepower. There's no way you're going to get there.
Yep. So here's a good. Go ahead.
And for years I've used the 3 hertz, as you can, I tell people, look, try going to 63 hertz and see what happens. You're not going to hurt anything if you're standing there watching it while you do it. And you're going to find out really quickly whether it'll work or not.
Yep.
And it all depends on the system dynamics. Understand, as you increase flow, what happens to our head loss in the system? It's going to go up, right? So everything changes exponentially. So, you got to understand the affinity laws really closely before you start just randomly going, okay, well, I'm going to jack it up 3 hertz. I don't like doing it if I don't have to. Now, you won't say I've never done it, but I'm cautious.
Yeah. So basically, here's another question. Great question. Kelvin's asked some really good ones here. So basically, you vary the frequency to change the speed of the motor, not the voltage the motor is required.
Exactly. There is so inside the VFD, there is a V over F ratio, which is voltage over frequency. And yes, as you decrease the frequency, you will decrease the voltage, but it is not as dramatic as you think it is. It's not like if I decrease the speed by 50%, I'm not cutting the voltage by 50%. It's nowhere close to that dramatic.
All right, so this is it's going to take me a while to read this one, but it's got a lot of info in it from Chris.
Okay.
An inverter may produce a square wave, sine wave, modified sine wave, pulsed sine wave, or near sine pulsed width modulated wave, PWM, depending on the circuit design. Common types of inverters produce square waves or quasi-square waves. Is that right? Holy moly!
Yes, that is the really long, complex answer to the output from an inverter. And it depends entirely on the inverter design and all the electronics that go into it. And I don't claim to be a master of all things VFDs. I've taught enough VFD classes. I've worked on VFDs enough in my career, worked with them enough in my career that I understand what they do, how they do it, why they do it. Do not ask me to get into the electronics design because I am not an electrical engineer. And nor do I want to be. I'm happy and content messing with stuff that I can see. Electrical engineers and electronics engineers, they design stuff that you don't get to see. And when you do get to see it, it's usually a bad thing. When the magic smoke gets out, it's all over.
There you go.
So, I understand VFDs because I kind of have to in what we do. And I can talk about them and I can talk about how to apply them and set them up and program them and do all that kind of neat stuff. But don't ask me in depth about the electronics inside of it. That's the electrical guys. Let them do that. Yes, there are different waveform outputs depending on the electronics that are controlling it. And it's all about controlling that waveform shape.
Yeah. Chris said, next seminar for that. We'll have to get a electrical guy for that one. We'll table that right now. Okay. Yeah. Bill says this is a pretty good statement. We like to use non-overloading pumps and motors. So we size VFD for the pump motor horsepower and balance with VFD and not the old multi-purpose valve. I changed that wording, Bill, just so you know. Of the last 3 words. Anyways,
he must use the acronym for one of the red guys.
Yeah,
and that's okay. Yep. We understand. We know what you mean. Yeah. So there are lots of thoughts to that, and yes, that is my preference as well, is to not use a balance valve of any type on the discharge of the pump, and adjust your speed accordingly. And that's what, if you use our self-sensing pumps, that is what ProBalance does, is it actually tunes the pump to the actual system dynamics. Because we know that as HVAC designers, when we design the piping system, the head loss calculations are our best estimate of what those losses are going to be based on how we envision the piping being laid out. Well, if the contractor lays it out differently, changes the number of fittings, goes from short radius to long radius or long radius to short radius, different type valves, all these things play into that head loss calculation. And it can change what the actual system head loss is. It also depends on how much safety factor you put in, okay? So what happens is when we design that system, and I design it for 2,000 GPM at 100 feet ahead. Well, what happens when there's only 90 feet ahead or 85 feet ahead? Well, with ProBalance, I can readjust that stealth sensing algorithm to control to those new values. With a VFD on there, I can slow the pump down to accommodate the new conditions. In olden days, way back when I started out, we just closed the multi-purpose valve down and add head loss to keep the pump running on its curve at the design point. Today, if you read what ASHRAE says you can't do that anymore. You're not allowed to do that. So the whole idea is that's why we've gotten away from using MPVs or the other guy's version of a multi-purpose valve on the discharge side of the pump for balancing anyway. Not to say you can't still use it for a check valve and an isolation valve, you just don't want to use it for balancing.
That's all we got question-wise, unless someone pops something else up. So I think we're going to sign off. Awesome.
Awesome.
Thank you so much, Jeff Maddox, Mark Amoros, good guys. The TACO reps. By the way, audience, this is my strong opinion. TACO has the best manufactured representatives in the business. We have a lot of long-term reps out there, and they are fantastic guys. If you haven't met your local TACO rep, make sure you do. I'm sure you always have, but they're fantastic. Tony, thank you. You want to say goodbye before I sign off?
Yes, and Brett, I will second that opinion. I've met a whole bunch of our reps, and as most of you know, I came from another pump company and dealt with other reps. TACO has the absolute best reps in the business. And I thank you for all your support. You guys are great. Everybody have a great Tuesday and enjoy the rest of your week.
Thanks, Tony. Enjoy that fine, cool weather down in Arizona.
Oh yeah.
Yeah. Go fry an egg on a rock.
Yeah.
Not on your head, on a rock. Thank
All
you,
right.
everybody. We will, there'll be a new announcement for the fourth quarter TACO Tuesdays. Hard to believe it's already almost September. Good Lord. Sad. Very sad. Very sad.
Yeah.
Anyways, have a great time. Look for that email tomorrow, and we will see you down the road. Goodbye, everybody. Thank you very much, Tony. Great job.
Thanks, guys.